Thank you very much for the invitation. It is a pleasure and an honor. And I would classify this talk as an applied algebraic geometry talk. And the applied part is with connections to machine learning. Okay, so I will directly define the problem of interest, unlabeled principal component analysis. We have a matrix X, which for now, let's take it to be a real matrix, m by n. And its rank is R. And let pi be a permutation of the matrix entries, could be any permutation. So x tilde is the permutation of x under that pi. Now, the question is very simple. What can we say about the recovery of x from x tilde? Can there be efficient algorithms? Now, there's one thing that we can immediately say. This is in remark 2. We can say that at best, we can recover x from its permuted version, x tilde, only up to a row and column permutation. The reason is that those permutations that permute the rows of x and the columns of x, they preserve the rank. And the only thing we know about x is the rank, that it has rank R. So there's no way to distinguish from a permuted version of x, from x itself, and a particular permutation of x of this form, pi 1 x, pi 2. Okay, now this problem, we have called it unlabeled principal component analysis. And so there are two notions that play a role here. And the arrows here, they should be permuted. This is humorous. So one notion is the PCA, the principal component analysis, and the other is the unlabeled part. And this comes from a recent subject called unlabeled sensing. So it's impossible to talk about unlabeled PCA without talking a little bit about these two, and in fact, more than a little bit for unlabeled sensing. But let's start with principal component analysis. So in principal component analysis, we have a matrix, x tilde, and the goal is to find a linear subspace V of R to the M of dimension R. So the matrix has size M by S. We want to find a linear subspace V of dimension R such that the columns of the matrix are close to V. I'm not specifying what close means. Okay, it can mean different things depending on what we want. In the noiseless case, then this subspace dimension R can be taken to be the rank of the matrix. V is the column space of the matrix, and the computation can be done by a singular value decomposition. Now, what if we have noise? If we have noise and data corruptions, principal component analysis becomes robust principal component analysis. And the setting is the following. There is a rank R ground truth matrix X. And what we observe is a corrupted version of X, X tilde. Now, there are three main kinds of corruptions that have been considered in the robust PCA literature. The first one is sparse noise. So the corrupted matrix X tilde is the ground truth rank R matrix X plus a sparse matrix E. And a typical way to try to extract X from X tilde, or the column space of X from X tilde, is to solve this convex optimization problem that I have in orange color, which says I'm going to minimize the nuclear norm of a matrix L plus another term, which is the difference of L from X tilde, and I want this, I place this term inside the one norm. So I want this to be sparse. Now, the nuclear norm of the matrix is the sum of its singular values, and it is the convex envelope of the rank function. So this is then trying to say that I want to find a low rank matrix L such that if I subtract it from the observed matrix X tilde, then I get a sparse matrix. So ideally, L should be equal to X in the solution of this problem. And indeed, there's a beautiful theory that describes conditions under which the optimal solution of this convex problem is X. The other type of corruption is we have additional points in our data set. So the ground truth Rankar matrix X is our data set. And then we have some additional points which are outliers. We don't want them. And so what we observe is a bigger matrix. It has the inliers and the outliers. Okay, can you hear me okay?
Yep.
Okay, thank you very much. Now this pi here is some permutation that permutes the columns of X tilde, just to tell us that we don't know which point is an inlier, we don't know what point is an outlier. Along the lines of the sparse noise, we can solve, it's typical to consider this convex optimization problem. We still search for a low rank matrix L, but now we want to have a matrix Y, okay, such as L, the low rank matrix, plus Y, their sum equals the observed matrix. And now Y is column sparse. So most of the columns of Y are 0. And that's why here I have put the so-called 2,1 norm. And this works, of course, if the matrix is low rank. However, in robust principal component analysis and in subspace learning, there's also the higher rank case. So I might want to recover a ground truth matrix whose rank is not so small. Then such a optimization problem would not work. And in contrast, here is one problem that works. So here, imagine that the rank of R is large, so the codimension of the column space of X is small. And thus, what we're saying here is we want to find a basis, an orthonormal basis, for the orthogonal complement of X. So I'm going to multiply X, the matrix. I'm going to take inner products with this potential orthogonal basis. And I want this vector, this matrix, after I take this inner product, I want it to be, to have sparse, to be sparse along the rows, because all the inliers are going to be orthogonal to this orthogonal basis B. So this is a co-sparse 1,2 problem, and it is non-convex because of this is a non-convex constraint. Now, this algorithm will play a role towards the end of this talk when I'm going to talk about an algorithm for unlabeled principal component analysis. So let's call this algorithm A. Okay, it is a robust PCA algorithm with robustness to outliers. A third kind of corruptions that has been considered is missing entries. So we have our ground truth matrix X, but we partially observe it on a mask omega. So here, omega is a matrix of the same size, but it is a 0-1 matrix. And this is the Hadamard product, point element by element product. And what it does is it keeps the entries of X with indexed by the elements of omega, and at other locations it puts zeros. A synonym of robust principal component analysis with robustness to missing entries is low rank matrix completion. It's exactly this problem. We have a partially observed Rankar matrix and we want to complete it. And here's a convex optimization problem that has been considered in the literature. I want to find a low rank matrix L that agrees with the observed matrix at the observed entries. Now, I'd like to say that this problem of low rank matrix completion is one of my favorite problems. So I could very well stop here talking about unlabeled principal component analysis and start talking about this, but perhaps another time. it has beautiful connections with algebraic geometry, commutative algebra, and combinatorics. So here's an interesting problem that relates to the low-rank matrix completion. And because it uses a piece of notation that I will need it anyway, I'm just mentioning it to you. So suppose that K is an infinite field, and let M, R, comma, M by N, to be the algebraic variety of matrices of size M by N of rank at most R. And let A to the omega be the affine space of dimension omega, or the set of M times N matrices with support in omega. So M by N matrices that has zeros outside of omega. And we can consider this coordinate projection. So we go from this variety of rank R matrices, we apply this mask omega, and then we go to this affine space. And the problem is, which coordinate projections have finite generic fiber? So this connects to algebraic matroids. To have finite fiber, it means to have finitely many completions. Okay, moving on. We can see now that a fourth kind of corruption can be permutations. And indeed, recently in the machine learning and signal processing literature, statistical as well, this has been considered with interest, because there are applications where, for example, in linear regression, where the input variables, the correspondence between the input variables and the output variables has been lost. There are applications like this in data mining and biology, several applications. So it's a natural, let's say, modern type of corruption to consider. Okay, now the other notion in unlabeled principal component analysis, besides principal component analysis, was unlabeled sensing. So what is unlabeled sensing? This was introduced by Unikrishnan, Hagigatswar, and Vetterli, starting from a paper, from a conference paper in 2015, which became a journal paper in 2018. And the problem is like this. We have a linear system of equations, AX equals B, where the coefficient matrix A, it has size M by R, and M is bigger than R, and the matrix A has rank R. And B is a vector in the column space of A. So this linear system of equations has a unique solution, which let's call it Xi. Now let pi be a permutation of R to the M. So it permutes the coordinates of R to the M. And let rho be a coordinate projection, which goes from Rm to Rs. And what it does, it just keeps S entries from a vector with M entries. Here's the problem of unlabeled sensing. Do the data A, the coefficient matrix, and a permuted and downsampled version of the right-hand side vector B uniquely define the solution Xi of the linear system of equations? In other words, can we still solve this linear system of equations after the right-hand side vector has been permuted and some of its entries have been thrown away? The main theorem of unlabeled sensing says yes, if the coefficient matrix is generic and the number of entries of the right-hand side vector that we observe, this is S, is at least twice the dimensionality of the solution Xi, this R. Now, interestingly, this is a special case of a more abstract phenomenon, which I have called homomorphic sensing. And I will briefly mention it because it might give you some ideas later on. So T is a finite set of endomorphisms of the vector space K to the M. And it consists of little tau i's, finite. V is a linear subspace of K to the M of dimension R. Now, here's a question. If I have two vectors, v1 and v2 in V, and I take two endomorphisms, tau1 and tau2, if the images of the two vectors, v1 and v2 under the two endomorphisms, tau1 and tau2, are equal, can we conclude that the vectors to begin with were equal? I call this homomorphic sensing property. And the case of unlabeled sensing, the problem of unlabeled sensing, essentially asks this question, but T is the set of permutations of K to the M. Okay, here's the main theorem of homomorphic sensing, on which I worked with my former master students, Liangzhu Peng. Let's consider a variety, an algebraic variety that depends on the two endomorphisms, tau1 and tau2. This is a variety of K to the M. And it is defined to be the variety of two minors of the following matrix. So here, T1 and T2 are matrix representations of the endomorphisms. And Z is a vector of M variables. So this matrix here has size M by 2. And then the variety is defined like this. We take all the two minors, 2 by 2 minors of this matrix, and the variety is the set of common solutions to these minors. In other words, it's the set of all points in K to the M, such that if I substitute the point here in the variables, the two vectors become linearly dependent, because this is exactly when the two minors vanish. Inside this variety, let's subtract a union of three linear spaces, which is also a little subspace arrangement. This is also a variety. So we subtract this. This is a harmless locus. And we get a locally closed set. So this U is an open set of the variety Y. So here's the theorem. If V is a generic R-dimensional linear subspace of dimension less or equal than the codimension of this open subscheme, then the homomorphic sensing property that I mentioned holds. And it turns out that in the case of unlabeled sensing, if we compute the dimension of this object, we get exactly the condition that the number of coordinates we observe from the right-hand side vector has to be at least twice the dimensionality of the solution. Moreover, this theory can be extended to subspace arrangements. So instead of having a linear subspace V, we can now have a union of linear subspaces. Okay, this is with regards to the abstraction of unlabeled sensing. Coming back to the unlabeled sensing, from an algorithmic point of view, there are various approaches, and I have not included them all here, just to give you an idea. It can be approached by dynamic programming, by branch and bound, by concave minimization, by L1 regression. I have to say here that when the permutation that when we know that the permutation is sparse, so in our vector, we know that just a few coordinates have been permuted. That makes a big difference. It makes the problem much more tractable. And there, Slowski and Ben David have done a lot of work theoretically and algorithmically. And it can even be solved with theoretical guarantees with L1 regression. Or another approach is with algebraic geometry. So I'd like to talk to you about this approach. Still, we are in unlabeled sensing, okay? Not in unlabeled principal component analysis yet. So we have the linear system of equations, AX equals B. Y is a permuted version of B. And we want from A and Y to get the solution psi of this system. Okay. We consider this a polynomial ring in M variables, as many as the rows of A. And those polynomials are what? Are the first R power sums of the variables Z1 up to Zm. And observe that if I look at the first, we have those identities, those equalities. Because the vector xi is equal to the vector y up to a permutation, they're not equal, but up to a permutation, they're equal. If I take the sum of the entries of A times xi, this will be equal to the sum of the entries of y. This is the equality for L equals 1. Now I can take the sum of the squares of the entries of A times xi, and this will be equal to the sum of the squares of the entries of y. And I keep going like this until I have as many equations as the dimension of the solution I'm looking for. This is exactly the number r. So, okay, we take r such, the first r power some polynomials. So here's a system then, a polynomial system of r equations in r unknowns. These are the polynomials. I have substituted z with a times w. So now this has become, this PL hat has become a polynomial in a smaller polynomial ring with r variables, w1 up to wr. Here's a theorem about this, joined with Ha-Yang Choi and Aldo Conca. If A is generic, then the variety defined by those R polynomials consists of finitely many points. In other words, it is a complete intersection for geometers. One of those points in there is the point that we want, this psi that we want. Let me give you some ideas in the proof. The reason is that the first R power some polynomials form a regular sequence. This is because the first R symmetric, elementary symmetric functions form a regular sequence. And now, this together with the Groebner basis theory, an application of the Groebner basis theory for weighted term orders, gives that our polynomials, the R polynomials and R unknowns that we want, is also a regular sequence. And I just want to note here, for the commutative algebraists and algebraic geometers in the audience, that we use weighted Groebner-based theory because those polynomials, the PI hats, are non-homogeneous. So indeed, they consist of a homogeneous term and a constant term. This is just a number. So this is a polynomial of degree L, and this is just a number. Okay. Now, here's this algorithm for unlabeled sensing, this algebraic geometry algorithm for unlabeled sensing, which I will also use later at the end of the talk. And I'd like to call this algorithm B. This algorithm B takes as input a linear subspace of k to the m of dimension r, and a vector y, which is the permutation of some vector b in this linear subspace V. And it gives us back the vector b, okay? I take the linear subspace V, I take a permuted version of some vector that I don't know in V, and the algorithm gives us back the vector B. The algorithm proceeds as follows. It solves this polynomial system of R equations in R unknowns. The polynomials have degree 1, 2, 3 up to R factorial. Then with a simple criterion, we pick the best root among R factorial many. And then we refine that root with alternating minimization by trying to fit that root to the vector y that we have observed. Let me show you an example how this algorithm works. If the dimension of the linear subspace is 4, and if we have 1,000 equations, so the linear system, the permuted linear system is of size 1,000 by 4, and then we add a little bit of noise, 40 decibels, then in 15 milliseconds, this algorithm gives us back the correct answer with a 0.4% estimation error. What is the catch? Well, this is not scalable. Think of the following. As the subspace dimension goes up, this polynomial system of equations is going to produce, in principle, over an algebraically closed field, say, R factorial solutions. So as R increases, we won't even be able to store the solutions as R increases because they are R factorial, let alone solve this system. This is why I think the next theorem is interesting. This is very recent progress from with colleagues here in the Chinese Academy of Sciences that says the following. Under the same hypothesis, if we take R+1 polynomials, so now we have a system of R+1 polynomials in R equation, in R unknowns, then the variety that they define consists of a single point, the solution that we're seeking. So before we took the first R power some polynomials, now we're taking the first R+1. And here's the challenge. Can we find efficient and robust algorithms for solving this system of, apologies, this should be R+1, not N+1. So of solving this polynomial system of R+1 equations in R unknowns. This is not so easy. And if you're interested, I encourage you to have a look at it. Okay, now we can start talking about unlabeled principal component analysis. So to summarize, it can be viewed as an extension of principal component and robust principal component analysis, where the corruption is permutations, or it can be viewed as an extension, generalization of unlabeled sensing from linear spaces to the determinantal variety of rank R matrices. Here's the recovery theorem. Suppose that X is a generic rank R matrix. This variety is irreducible, so certainly we can talk about a generic rank R matrix. Another way to think of it is take a matrix B, which has size B by R, take a matrix C, which has size R by M, select them randomly, and then multiply them. Then this is going to give you a generic matrix of rank R. Let pi be any permutation of the matrix entries. Then the rank of the permuted matrix is equal to R if and only if the permuted matrix is a row and column permutation of X, or if the permuted version of X is the transpose of X in case M is equal to N. So what this theorem says is that up to a row and column permutation, X is the only rank R matrix that agrees with pi of X. So a brute force way of recovering X from its permuted version is to try all permutations. Start trying permutations. There are m times n factorial of them, so this could be a huge number, but start taking permutations. And the moment you find a matrix that has R, rank R, this is going to be a row and column permuted version of X. And that is okay, because in applications, X is a data matrix. So along its rows, we see features. Along its columns, we see subjects. So it could be, for example, on the columns, we could have patients. In the rows, we could have gene expressions. So if you permute the rows and if you permute the columns, it's fine. The same information is there. Now, let me give you a sketch of the proof of this theorem.
just before you do, I noticed
Yes.
there's a question in the chat. Just a second whilst I try and find it.
Yeah, please, please.
Here we are. Yeah. So Catholic asks, what's a generic matrix?
Right. So, very good. So here, so I'm going to answer in two ways. I'm going to answer in a data science way, and I'm going to answer in an algebraic geometry way. So let's first answer the data science way. Data science way is the following. I take a matrix of size M by R. We know that every rank R matrix can be factored as the product of a tall matrix of size M by R and a fat matrix of size R by N. So randomly pick B and randomly pick C. So go to MATLAB and use the random function, for example, and multiply those two. Take the product B times C. Then this is a generic matrix of rank R. And if you have a matrix like this, the statement of the theorem is true. Now, let me give the algebraic geometry answer. This space of rank R, of at most rank R matrices, is a variety. It is defined by polynomials of degree R plus 1. They are the R plus 1 by R plus 1 minors of the matrix. And the matrix has rank R if and only if all R plus 1 by R plus 1 minors of the matrix are 0. And it is an irreducible variety. What is the consequence of the irreducible variety in the Zariski topology now, okay? The consequence is that if we have a closed set, so say some weird space inside this variety that is defined by some polynomial equations. So if we have a closed set inside this variety, the complement of it, so the set of matrices which do not satisfy those equations, is open, and in particular, it is dense. So then what I mean by generic in an algebraic geometry sense is that there is a closed subvariety of this determinantal variety of at most rank R matrices, such that for every rank R matrix outside of this closed subvariety, the statement of the theorem is true. How has that answered the question? Is it okay?
Yes, thank you.
Brilliant. Cheers.
Okay. Thank you. All right, now let me give you a sketch with regards to the proof of this theorem. Let's consider a matrix of variables Z. So this has size M by N, the same as the size of our matrix X. And let's consider a polynomial ring, K bracket Z, of dimension M times N. So this is just a polynomial ring in the variables Zij's, where I goes from 1 up to M, the number of rows, and J goes from 1 up to N, the number of columns. Inside there, let us consider the ideal generated by all R plus 1 by R plus 1 determinants of Z. So what is the ideal? Is the set of all linear combinations of the R plus 1 by R plus 1 determinants of this matrix of variables, but now the coefficients are arbitrary polynomials in the variables Z. So the set of all such polynomials forms something that is called ideal. Let's consider this ideal. There is this very important and famous theorem in the field of commutative algebra, proved by various people with different techniques. So here I mentioned some. I'm not sure if it covers all of them, but it seems that the first one to prove it was Narasimhan in 1986. And it says the following: the R plus 1 minors of Z are a Groebner basis for the ideal of R plus 1 minors under any diagonal or anti-diagonal term order. In particular, from this we can get knowledge of what is the initial ideal, and so on. I will not enter too much into detail. I'll just say that a Groebner basis for this ideal, or for any ideal, but let's say for this ideal, is a set of generators whose initial monomial, so if we put an order on the monomials, so their initial monomials also generates the initial ideal of this ideal. And what is the initial ideal? It is, I look at all the polynomials in the ideal, and then I pick the leading term from each polynomial. And then this makes the initial ideal. It doesn't matter. It's rather technical for this talk. However, from the fact that we can control the initial ideal like this, from the r+1 by r+1 minors, we can prove easily, immediately, I would say, that the set of rank R matrices such that they stay of rank R after a permutation is a proper subvariety of the variety of rank R matrices, except when the permutation permutes only rows and columns. And this fits with the intuition. If you have a matrix of rank R and you permute the entries, probably the rank will go up. So this is a formal expression of this fact. So one more time, the set of matrices of rank R, such that if I permute them with some permutation, they also stay of rank R, is a proper subvariety of the variety of rank R matrices, except when the permutation is this innocent permutation. Doing this for, yes, so for this particular permutation pi, then, I can look at the complement of this proper subvariety, which gives me a dense open set. Doing this for every permutation, we have finitely many of them, we get finitely many dense open sets. A property of the Zariski topology is that in an irreducible space, if we intersect finitely many non-empty open sets, they will stay non-empty, open, and dense. And this is what gives us this dense open set. And this is the locus of generic matrices for this problem. Okay. Now, let's do something similar that we did before in unlabeled sensing. Let's consider the power sum polynomials, this time in as many variables as we have in the matrix. So the nth power sum polynomial is the sum of the nth powers of all matrix entries. And let J be the ideal of our polynomial ring, K bracket Z, generated by those. Equivalently, we may look at the solution sets to those polynomial equations. Okay. Here's a remark. With X generic, as explained, we can see easily from the theorem that I mentioned that the variety defined by the ideal of r+1 minors and the ideal of those power sum polynomials consists only of X together with its innocent permutations. So let me mention a fact that can be proved easily. If I have a vector of size S and I take the S power sum polynomials of that vector, I evaluate them, then those values uniquely determine that vector up to permutation. Okay. So this is what has been used here. So here I have the variety that wants to that wants to satisfy the r+1 by r+1 minors of Z, so rank R matrices. And here I have the variety that here. So interestingly, if you note, there is a nowhere here is X. So this remark is not very accurate as stated. I should have done this thing. It's a typo and I apologize. I should have said, I take the power sum, I evaluate it, I should take the difference of P1Z minus P1X, and then Pm times Nz minus Pmnx. In other words, those should be hats. Let me go back to unlabeled sensing. Right, so if you see here, I took the elf power sums. So these are just polynomials in variable Z. And then I substituted A times a variable minus the evaluation of that polynomial at the observed data. So I should have done the same thing for the unlabeled PCA case. Here should be PL of X, and here should be PL of Z, and I should be taking their difference. And this is PL hat. So with this remark, if we take those polynomials, the power sums, and take the variety they define, and we intersect that variety with the variety of rank R matrices, then what we will see is just X in its innocent permutations, which are row and column permutations of X. Put it in another way, I have the determinantal variety, and I intersect it with M times N hypersurfaces. Each polynomial defines a hypersurface. What I will see, these hypersurfaces will cut the variety of rank R matrices to X and all its innocent permutations. Now, this variety has dimension. It's very well known what is the dimension of this variety. It is R, the rank, times the number of rows plus the number of columns minus 1. So in this remark that I mentioned, we cut a variety of dimension R times M plus N minus R should be by M times N hypersurfaces. So this is too much. So here's a more economic result. Suppose that X is generic as before. Pi is any permutation of the matrix entries. Then, if I take dimension many plus 1 generic linear combinations of those power sum polynomials, this should be hats, this should be the hats here, they will cut, set theoretically, all the points, they will cut the determinantal variety at X and all its innocent permutations. So if I cut with dimension many hypersurfaces, dimension many, I will get finitely many points. So I will get X, its innocent permutations, and maybe some other garbage points. But if I cut with one more generic linear combination, then the garbage points will be removed. So quick sketch. Another famous result about this determinantal variety is that the quotient ring is Cohen-Macaulay. And moreover, another general fact is if I have an Noetherian ring that contains an infinite field, K, and I have an ideal I generated by S elements, alpha 1 up to alpha S, of positive grade. So the grade of the ideal is the length of a maximal regular sequence in I. Then, if I take a generic linear combination of the generators of the ideal, they will give me an element of the ideal alpha, which is regular on the ring. So it's not a zero divisor. And let me anticipate a question and explain what generic linear combination means. So it means that, again, here we have S generators. So we have the space of coefficients of the generators is a K to the S. So there is a subvariety of K to the S, which is a bad locus. And outside of this bad locus, every choice of C1 up to Cs gives me a regular element. Okay, so now, in the last few minutes of this talk, I will talk about a special case of UPCA where the problem is actually tractable computationally. And we worked on that with my former master students, Yunjian Yao and Liang Zupeng. And this special case of UPCA can be summarized like this, under the slogan, column-wise permutations with a dominant permutation. So what does that mean? If we take our rank R matrix, X, and we write it in column form, we assume that the permutation of X acts column-wise. So elements across columns are not being swapped, only elements in the same column. So here the pi 1 up to pi n is just a permutation that permutes the column, the entries of the column. And let's define the multiplicity of a permutation as the number of times this permutation occurs. So here you see we have pi 1, pi 2, pi 3, up to pi n. Some of them might be equal. Maybe pi 1 is equal to pi 2. So we can count how many times a permutation appears. And this number, we call it the multiplicity of the permutation. So let's assume that there is a permutation which is dominant. So it appears many more times than all other permutations. So the multiplicity of some pi j is much bigger than the multiplicity of pi j prime. For every pi j prime different than pi j. This implies the following. This implies that the matrix we observe, pi of x, has the following structure. It consists of a submatrix up to a column permutation here, pi, okay? This is harmless. So it consists of a column submatrix x tilde prime, which are those columns of x that have been permuted by the same permutation. Since the columns of x lie in the column space of x, the permuted columns will lie in the permuted subspace. So we have a big submatrix, column submatrix of pi x, which is of rank R because it lies in a subspace of rank R, the permutation of the column space of x. And then we have another matrix which consists of the original columns of x, which have now been permuted, but each column with a different permutation possibly. And for this reason, there's no particular structure here in this O matrix. And so this column submatrix now can be viewed as outliers. But now this is familiar. This is exactly the data matrix structure that one has when it's encountered in the PCA problem with robustness to outliers. So based on this, we can have an algorithm for unlabeled principal component analysis. The algorithm works like this. It takes the permuted version of x, and using algorithm A, if you remember, this is PCA with robustness to outliers. It produces a linear subspace of dimension R that is as close as possible to a big chunk of x. Then we have two things. We have the permuted version of x and this linear subspace. This linear subspace can be viewed as an estimate of pi j of column of x. But now, since we have a subspace, we have the permuted data, and we have a subspace, that's exactly what unlabeled sensing does. We can fit this to an unlabeled sensing algorithm, say this algorithm I described with the power sums. And this can give us back an estimate of X. All in all, in the algorithm, the input is a permuted version of X, and the output is an estimate of X. So let me show you in the last two examples, how does this work? So here we see three figures, and each figure corresponds to a different dimension. So in the first figure, the dimension is 3. In the middle, the dimension is 4. Last, the dimension is 5. This is the dimension of the linear subspace, whose the dimension of the of the column space of X. So you can think of it as the rank. Okay. In the horizontal axis, we have outlier ratio. This tells us how many outliers we have, or in this context, for example, let's look at this 75%. Then this tells us that 25% of the columns have been permuted by the same permutation, but not more. So only 25% are the inliers, and the rest are outliers. And in the vertical axis, it is the estimation error. So it is the ground truth matrix X, here it's called X star, okay? So it's difference from the output of the algorithm, X hat, and then relative error. So you see that as the rank increases, the estimation error goes up. And the blue is this algebraic geometry algorithm that I mentioned. So the blue is algorithm A together with algorithm B. And the red is using another algorithm for unlabeled sensing. Finally, let me show you something fun. We did the following experiment. We worked with a face database where each column of the data matrix is a vectorized version of a face image. So this is a face image. We vectorize it, and this becomes one of the columns of the matrix. The faces come from the same individual. This is the Yale, extended Yale B database. So the person is the same, the pose is the same, and all that varies across different face images is the illumination. And it is known and proved theoretically in computer vision that if the pose is fixed and only the illumination varies, if I do this thing, if I vectorize the face images, put them in a matrix, and I calculate the rank, then the rank is going to be very small. It's going to be, the theoretical rank is 8. While the image might be very big. It may have 1,000 pixels, or in the particular case, maybe 200. But the rank is going to be very small. So we do this, and we create like this our data, ground truth data, rank 8 matrix X. And then we go to a subset of the columns of X, and we apply various types of permutations. So these are the various types. So we can permute everything, but with big permutation blocks. We can permute everything, dense permutations, but smaller blocks. Then we can have a partial permutation with bigger chunks, or a partial permutation with smaller chunks. And we do this only for a part of the columns. And then we apply this UPCA algorithm that I described, and here's the result. As you can see, the recovery is pretty good. And I'd like to stress out again that in algorithm A, the subspace estimation was done by this non-convex method that tries to find the orthogonal complement. And the algorithm B for the unlabeled sensing part was done by this algebraic geometry algorithm using the power sum polynomials. And with this, thank you very much. I talked about many things, so please ask me anything that might be interest to you. Thank you.